Hello everyone. Today we will read the chapter number 10 of NCERT Class 11 from the book Fundamentals of Physical Geography. Chapter 10, Atmospheric Circulation and Weather System. So let's get started. Earlier chapter 9 described the uneven distribution of temperature over the surface of the earth. Air expands when heated and gets compressed when cooled. This results in variations in the atmospheric pressure. The result is that it causes the movement of air from high pressure to low pressure, setting the air in motion. You already know that the air is horizontal. The air in horizontal motion is wind. Atmospheric pressure also determines when the air will rise or sink. The wind redistributes the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. The vertical rising of moist air cools it down to form the clouds and bring precipitation. This chapter has been devoted to explain the causes of pressure differences, the forces that control the atmospheric circulation, the turbulent pattern of wind, the formation of air masses, the disturbed weather when air masses interact with each other, and the phenomenon of violent tropical storms. Next point is atmospheric pressure. Do you realize that our body is subjected to a lot of air pressure? As one moves up, the air gets verified and one feels breathless. The weight of a column of air contained in a unit area from the mean sea level to the top of the atmosphere is called the atmospheric pressure. The atmospheric pressure is expressed in units of millibar. At sea level, the average atmospheric pressure is 1013.2 millibar. Due to gravity, the air at the surface is denser and hence has higher pressure. The air pressure is measured with the help of mercury barometer or the aneroid barometer. Consult your book Practical Work in Geography Part 1 NCERT and learn about these instruments. The pressure decreases with height. At any elevation, it varies from place to place and its variation is the primary cause of air motion. Wind, which moves from high pressure areas to low pressure areas. Next point is vertical variation of pressure. In the lower atmosphere, the pressure decreases rapidly with height. The decrease amounts to about 1 mb for each 10 meter increase in elevation. It does not always decrease at the same rate. Table 10.1 gives the average pressure and temperature at selected levels of elevation. In sea level, air pressure is 1013.25 millibar and temperature is 15.2. At 1 kilometer height, the pressure is 898.76 millibar and the temperature is 8.7. In 5 kilometer, the pressure is 540.48 millibar and temperature is minus 17.3. In 10 kilometer, above the 10 kilometer, the pressure is 265 millibar and the temperature is minus 49.7. The vertical pressure gradient force is much larger than that of horizontal pressure gradient, but it is generally balanced by a nearly equal but opposite gravitational force. Hence, we do not experience strong upward winds. Next point is horizontal distribution of pressure. Small differences in pressure are highly significant in terms of wind direction and velocity. Horizontal distribution of pressure is studied by drawing isobars at constant levels. Isobars are lines connecting places having equal pressure. In order to eliminate the effect of altitude on pressure, it is measured at any station after being reduced to sea level for purposes of comparison. The sea level pressure distribution is shown on weather maps. Figure 10.1 shows the pattern of isobars corresponding to pressure systems. Low pressure system is enclosed by one or more isobars with the lowest pressure in the center. High pressure system is also enclosed by one or more isobars with the highest pressures in the center. Next point is world distribution of sea level pressure. The world distribution of sea level pressure in January and July has been shown in figure 10.2 and 10.3. Near the equator, sea level pressure is low and the area is known as equatorial low. Along 30° north and south are found the high pressure areas known as subtropical highs. Further polewards along 60° north and 60° south, the low pressure belts are termed as the subpolar lows. Near the poles, the pressure is high and it is known as the polar high. These pressure belts are not permanent in nature. They oscillate with the apparent movement of the sun. In the northern hemisphere, in winter they move southward and in the summer in northward. Next point is forces affecting the velocity and direction of wind. You already know that the earth is set in motion due to differences in atmospheric pressure. The air is motion is called wind. The wind blows from high pressure to low pressure. The wind at the surface experiences friction. In addition, rotation of the earth also affects the wind movement. The force exerted by the rotation of the earth is known as the Coriolis force. Thus, the horizontal winds near the earth's surface respond to the combined effect of three forces: the pressure gradient force, the frictional force, and the Coriolis force. In addition, the gravitational force acts downward. Next point, first point is pressure gradient force. The differences in atmospheric pressure produces a force. The rate of change of pressure with respect to distance is the pressure gradient. The pressure gradient is strong where the isobars are close to each other and is weak where the isobars are apart. Next point is frictional force. It affects the speed of wind. It is greatest at the surface and its influence generally extends up to an elevation of 1 to 3 km. Over the sea surface, the friction is minimal. Coriolis force, the rotation of the earth about its axis, affects the direction of wind. The force is called Coriolis force after the French physicist who described it in 1844. It deflects the wind to the right direction in the northern hemisphere and to the left in the southern hemisphere. The deflection is more when the wind velocity is high. The Coriolis force is directly proportional to the angle of latitude. It is maximum at the poles and absent at the equator. The Coriolis force acts perpendicular to the pressure gradient force. The pressure gradient force is perpendicular to an isobars. The higher the pressure gradient force, the more is the velocity of the wind and the larger is the deflection in the direction of wind. As a result of these two forces operating perpendicular to each other in the low pressure areas, the wind blows around it. At the equator, the Coriolis force is 0 and the wind blows perpendicular to the isobars. The low pressure gets filled instead of getting intensified. This is the reason why tropical cyclones are not formed near the equator. Next point is pressure and wind. The velocity and direction of wind are the net result of the wind generating forces. The winds in the upper atmosphere 2 to 3 km above the surface are free from frictional effect of the surface, are controlled by mainly by the pressure gradient and Coriolis force. When isobars are straight and when there is no friction, the pressure gradient force is balanced by the Coriolis force and the resultant wind blows parallel to the isobars. The wind is known as geostrophic wind. The wind circulation around a low is called cyclonic circulation. Around a high is called anticyclonic circulation. The direction of winds around such systems changes according to their location in different hemispheres. The wind circulation at the Earth's surface around low and high on many occasions is closely related to the wind circulation at higher level. Generally, over low pressure area, the air will converge and rise. Over high pressure area, the air will subside from above and diverge at the surface. Apart from convergence, some eddies, convection currents, orographic uplift and uplift along fronts cause the rising of air, which is essential for the formation of clouds and precipitation. Next point is general circulation of the atmosphere. The pattern of planetary winds largely depends on latitudinal variation of atmospheric heating, emergence of pressure belts, the migrants of belts following apparent path of the sun, the distribution of continents and oceans, the rotation of the earth. The pattern of movement of the planetary winds is called the general circulation of the atmosphere. The general circulation of the atmosphere also sets in motion the ocean water circulation, which influences the Earth's climate. A schematic description of general circulation is shown in the figure 10.6. Next point is pattern of wind direction in cyclones and anticyclones. Cyclone, pressure system cyclone, pressure condition at the center is low, and in case of anticyclone, pressure condition at the center is high. Pattern of wind direction: northern hemisphere cyclone anti-clockwise and southern hemisphere cyclone is in clockwise direction, and in northern hemisphere anticyclone is in clockwise direction, and in southern hemisphere anticyclone blows in anti-clockwise direction. Next point, next is the air at the intertropical convergence zone. The air at the intertropical convergence zones rises because of convection caused by high insolation, and a low pressure is created. The winds from the tropics converge at this low pressure zone. The converged air rises along with the convective shell. It reaches the top of the troposphere up to an altitude of 14 km and moves towards the poles. This causes accumulation of air at about 30 degrees north and south. Part of accumulated air sinks to the ground and forms a subtropical high. Another reason for sinking is cooling of air when it reaches 30 degrees north and south latitude. Down below near the land surface, the air flows towards the equator as the easterlies. The easterlies from either side of equator converge in the intertropical convergence zone. Such circulation from the surface upwards and vice versa are called sails. Such a sail in the tropics is called Hadley sail. In the middle latitudes, the circulation is that of sinking cold air that comes from the poles and the rising warm air that blows from the subtropical high. At the surface, these winds are called westerlies and the sail is called furl sail. At polar latitudes, the cold, dense air subsides near the poles and blows towards the middle latitudes as the polar easterlies. This sail is called polar sail. These three sails set the pattern for general circulation of the atmosphere. The transfer of heat energy from lower latitudes to higher latitudes maintains the general circulation. The general circulation of atmosphere also affects the ocean. The large-scale winds of the atmosphere initiate large and slow-moving currents of the ocean. Oceans in turn provide input of energy and water vapor into the air. These interactions take place rather slowly over a large part of the ocean. Next point in box is general atmospheric circulation and its effects on oceans. Warming and cooling of Pacific Ocean is most important in terms of general atmospheric circulation. The warm water of Central Pacific Ocean slowly drifts towards South American coast and replaces the cold Peruvian current. Such appearance of warm water off the coast of Peru is known as El Nino. El Nino event is closely associated with the pressure changes in the Central Pacific and Australia. This change in pressure condition over Pacific is known as the Southern Oscillation. The combined phenomenon of Southern Oscillation and El Nino is known as El Nino and Southern Oscillation. In the years when El Nino and Southern Oscillation is strong, large-scale variations in weather occur over the world. The arid west coast of South America receives heavy rainfall. Drought occurs in Australia and sometimes in India and floods in China. This phenomenon is closely monitored and is used for long-range forecasting in major parts of the world. Next point is seasonal wind. The pattern of wind circulation is modified in different seasons due to shifting of regions of maximum heating, pressure and wind belts. The most pronounced effect of such shift is noticed in the monsoon, especially over the Southeast Asia. You would be studying the details of monsoon in the book India Physical Environment. The other local deviations from the general circulation system are as follows. First point is local winds. Differences in the heating and cooling of earth surfaces and the cycles those develop daily or annually can create several common local and regional winds. Land and sea breezes. As explained earlier, the land and sea absorb and transfer heat differently. During the day, the land heats up faster and becomes warmer than the sea. Therefore, over the land, the air rises, giving rise to a low pressure area, whereas the sea is relatively cool and the pressure over the sea is relatively high. This pressure gradient from sea to land is created and the wind blows from the sea to the land as sea breeze. In the night, the reversal of condition takes place. The land loses heat faster and is cooler than the sea. The pressure gradient is from land to sea and hence land breeze results. Next point is mountain and valley wind. In mountainous regions during the day, the slopes get heated up and air moves upslope and fill the resulting gap. The air from the valley blows up the valley. This wind is known as valley breeze. During the night, the slopes get cooled and the dense air descends into the valley as the mountain wind. The cool air of the high plateaus and the ice fields draining into the valley is called katabatic wind. Another type of warm wind occurs on the leeward side of mountain ranges. The moisture in these winds while crossing the mountain ranges ranges condense and precipitates. When it descends down the leeward side of slope, the dry air gets warmed up by adiabatic process. This dry air may melt the snow in a short time. Next point is air masses. When the air remains over a homogeneous area for a sufficiently longer time, it acquires the characteristics of the area. The homogeneous regions can be the vast ocean surface or vast plains. The air with distinctive characteristics in terms of temperature and humidity is called an air mass. It is defined as a large body of air having little horizontal variation in temperature and moisture. The homogeneous surfaces over which air masses form are called the source regions. The air masses are classified according to the source regions. There are 5 major source regions. These are warm tropical and subtropical oceans, the subtropical hot deserts, the relatively cold high latitude oceans, the very cold snow covered continents in high latitudes, permanently ice covered continents in the Arctic and Antarctica. Accordingly, following types of air masses are recognized: maritime tropical or MT, continental tropical CT, maritime polar MP, continental polar CP, continental Arctic CA. Tropical air masses are warm and polar air masses are cold. Next point is fronts. When two different air masses meet, the boundary zone between them is called the front. The process of formation of the front is called frontogenesis. There are 4 types of fronts: cold, warm, stationary and occluded. When the front remains stationary, it is called stationary front. When the cold air moves towards then the warm air mass, its contact zone is called the cold front. Whereas if the warm air mass moves towards the cold air mass, the contact zone is a warm front. If the air mass is fully lifted above the land surface, it is called occluded front. The fronts occur in middle latitudes and are characterized by steep gradient in temperature and pressure. They bring abrupt changes in temperature and cause the air to rise to form clouds and cause precipitation. Next point is extratropical cyclones. The system developing in the mid and high latitude beyond the tropics are called the middle latitude or extratropical cyclones. The passage of front causes abrupt changes in the weather conditions over the area in the middle and high latitudes. Extratropical cyclones form along the polar front. Initially, the front is stationary. In the northern hemisphere, warm air blows from the south and cold air from the north of the front. When the pressure drops along the front, the warm air moves northward and the cold air moves towards south, setting in motion an anti-clockwise cyclonic circulation. The cyclonic circulation leads to a well-developed extratropical cyclone with a warm front and a cold front. The plan and cross section of a well-developed cyclone is given in the figure 10.9. There are pockets of warm air or warm sector wedged between the forward and the rear cold air or cold sector. The warm air glides over the cold air and a sequence of clouds appear over the sky ahead of warm front and cause precipitation. The cold front approaches the warm air from behind and pushes the warm air up. As a result, cumulus clouds develop along the cold front. The cold front moves faster than the warm front, ultimately overtaking the warm front. The warm air is completely lifted up and the front is occluded and the cyclone dissipates. The process of wind circulation both at the surface and aloft are closely interlinked. The extratropical cyclone differs from the tropical cyclone in number of ways. The extratropical cyclones have a clear frontal system which is not present in the tropical cyclones. They cover a larger area and can originate over the land and sea, whereas the tropical cyclones originate only over the sea and on reaching the land they dissipate. The extratropical cyclone affects a much larger area as compared to tropical cyclone. The wind velocity in the tropical cyclone is much higher and is more destructive. The extratropical cyclones move from west to east, but tropical cyclones move from east to west. Next point is tropical cyclone. Tropical cyclones are violent storms that originate over oceans in tropical areas and move over to the coastal areas, bringing about large-scale destruction caused by violent winds, very heavy rainfall and storm surges. This is one of the most devastating natural calamities. They are known as cyclones in Indian Oceans, hurricanes in Atlantic, typhoon in the Western Pacific and the Southern China Sea, and willies in the Western Australia. Tropical cyclones originate and intensify over warm tropical oceans. The conditions favorable for formation of and intensification of tropical storms are large sea surface with the temperature higher than 27 degrees Celsius, presence of Coriolis force, small variation in the vertical wind speed, a pre-existing weak low pressure area or low level cyclonic circulation, upper divergence above the sea level system. The energy that intensifies the storm comes from condensation process in the towering cumulonimbus clouds surrounding the center of the storm. With continuous supply of moisture from sea, the storm is further strengthened. On reaching the land, the moisture supply is cut off and the storm dissipates. The place where a tropical cyclone crosses the coast is called the landfall of the cyclone. The cyclones which cross 20° north latitude generally recurve and they are more destructive. A schematic representation of the vertical structure of a mature tropical cyclonic storm is shown in figure 10.10. A mature tropical cyclone is characterized by strong spirally circulating wind around the center called the eye. The diameter of the circulating system can vary between 150 to 250 km. The eye is a region of calm with subsiding air. Around the eye is the eye wall, where there is a strong spiraling ascent of air to greater height, reaching the tropopause. The wind reaches maximum velocity in this region, reaching as high as 250 km per hour. Torrential rain occurs here. From the eye wall, rain bands may radiate and trains of cumulus and cumulonimbus clouds may drift into the outer region. The diameter of the storm over the Bay of Bengal and Arabian and Indian Ocean is between 600 to 1200 km. The system moves slowly. About 300 to 500 km per day. The cyclone creates storm surges and inundate the coastal lowlands. The storm peters out on the land. Next and last point is thunderstorms and tornadoes. Other several local storms are thunderstorms and tornadoes. They are of short duration, occurring over a small area but are violent. Thunderstorms are caused by intense convection on moist hot days. A thunderstorm is a well-grown cumulonimbus cloud producing thunder and lightning. When the clouds extend to a height where sub-zero temperatures prevails, hails are formed and they come down as hailstorm. If there is insufficient moisture, a thunderstorm can generate dust storms. A thunderstorm is characterized by intense updraft of rising warm air, which causes the clouds to grow bigger and rise to greater height. This causes precipitation. Later, downdraft brings down to earth the cool air and the rain. From severe thunderstorms, sometimes spiraling wind descends like a trunk of an elephant with great force, with very low pressure at the center, causing massive destruction on its way. Such a phenomenon is called a tornado. Tornadoes generally occur in middle latitudes. The tornado over the sea is called water spouts. These violent storms are the manifestation of the atmosphere's adjustments to varying energy distribution. The potential and heat energies are converted into kinetic energy in these storms, and the restless atmosphere again returns to its stable state. So thank you for listening. This is for today. Thank you.